Dear students, in this lecture we will discuss about superposition theorem and its application on the electrical circuits to solve to determine the response of the electrical circuits. So this lecture covers an introduction to the superposition theorem and the procedure to solve an electrical circuit using superposition theorem. Now let us come to the introduction to the superposition theorem. A superposition theorem is basically a mathematical tool which is used in electrical systems to solve the complex electrical networks. And it provides us a more elaborated way to understand the response of the electrical circuits in more convenient manner. Superposition theorem is basically applicable to the linear electrical circuits only because superposition theorem is based on the concept of linearity or concept of superposition. And linear circuits are those electrical circuits which obey the principle of superposition and homogeneity. Now, as far as the statement of this theorem is concerned, so this theorem states that in any electrical network which contains two or more than two electrical sources, whether the voltage sources or the current sources or both. So in such type of network, if we have to find out the current or voltage through or across any branch of the circuit, so the net effect, net current or net voltage in that branch would be the algebraic sum of effects produced by each source in that branch when the source acts individually. What does it mean? It means that if we have, let us say, two sources in an electric circuit, so we have to find out the current through any branch. So let us take one circuit here. So let us have this circuit. Uh, there is a circuit, a simple circuit we will take. We have a resistance here. We have a resistance here. And then let us say we also have a resistance here, and then this is a voltage source, right? So this is, let us say, E1, and this is E2, and this is R1 and R2 and R3. Now as per the statement of this theorem, the current, let us say the current in this is I1, for example, the current in this is I2, and the current in this is I3, for example. So this I1 is basically not because of E1 only, it is because of E1 as well as E2. This I2 is because of both sources. This I3 is also because of both sources. So I3, I1 is the algebraic sum of i's produced by E1 and E2 in R1, right? Similarly, we can understand with I2 also and I3 also, right? Now, when we say that I1 is the algebraic sum of the currents produced by E1 and E2, so that means we need to find out by taking one source at a time, right? So we will not take both the sources, so we will take only one source at a time. We will keep other source deactivated. Now when we say deactivation of the sources, so that means keep one source and deactivate all other sources in the circuit, right? So similar step would be applied to each and every for each and every source, right? Now, now when we say deactivating a source, so deactivating a source means replacing the sources uh, replacing the sources with their internal resistances. So, okay, so a voltage source has a practically very negligible resistance, and ideally it has zero resistance, and a current source practically has very high resistance, and ideally it has infinite resistance, right? So that means in any branch you can find out the current using superposition theorem, which has two or more than two uh, energy sources. Now let us see the procedure to solve an electrical network using superposition theorem. The first step is that we will select one source in the circuit at a time, and we will replace all the other sources, energy sources, with their internal resistances. Ideal voltage sources can be replaced with the short circuits, and ideal current source are replaced with the open circuit. So short circuit means zero resistance. That means if we have a voltage source somewhere in the circuit and we want to replace it, so let us say these two terminals are AB, so we will make this voltage source short, right? Because the internal resistance of this is zero, right? Similarly, the current source, if we have a current source between any two terminal of the network and we want to apply the superposition theorem, so this can be this is ideal. If it is ideal, so this can be replaced with an open path. So this is open, so Ri here is infinite, right? Now let us go to the third step. So, second step, sorry. Uh, Now we will determine the voltage or current through the desired element branch due to a single source. Now, whichever source we have selected as per this step one, we will try to calculate the voltage or current. See, we can calculate voltage across any element, circuit element, or we can calculate the current through any circuit element using this particular theorem, right? Now, uh, whichever branch we are assuming as a load branch, or whichever branch we have been asked to determine the voltage or current, so we can calculate the voltage and current using any method, like you can use current division rule or voltage division rule or source transformation or KVL or KCL, mesh node, whatever, whichever is applicable, you can apply that particular method and you can calculate the current or voltage through the desired branch, right? Please remember that when you apply step one on the circuit, redraw the circuit, right? Okay. Now let us go to third. Now we'll repeat the same thing, step one and step two for each of the source. Okay, we'll take one source at a time and we will replace all the sources with their resistances. We calculate the current through the required branch using any method, KVL, KCL, node, mesh, current division rule, voltage division rule, whatever, right? Now, the last step is once we have got all the currents because of all the uh, sources, so we will add them algebraically. Now, when we say add them algebraically, we have to take care of the direction, right? So, direction of V or I, right? Now, so adding them algebraic will give us the net effect in the branch, net current in the branch. This theorem is called as superposition because we what we are doing actually, we are superposing all the currents in a particular branch, right? We are adding them algebraically to get the net effect in the circuit. So let us understand this with the help of an example. So let us consider a circuit as shown here. In this circuit, we have two energy sources. One energy source is uh, a current source, then we have a voltage source here, and we have some resistances connected. Now we are asked to find out the current through 5 ohm resistance. So this is the 5 ohm resistance. So this is the load resistance basically in this case, right? So we will mark the nodes here. Let us say this is A, this is B, this is C, this is D, and then we have E, F, G and H. We have the marking here. Now we can calculate the current 5 ohm. So let us assume that this direction, this current is I, and the direction is this one. So this is our assumption. I am assuming, uh, let us assume that the net current in 5 ohm is I, and its direction is from B to C. So this is my assumption, purely assumption, right? Now, what we will do, we will keep one source activated, any one of them, let this one or this one, and we will deactivate the other source, and then we will redraw the circuit. Now, let us go to the step one here. So now let us calculate the current through 5 ohm resistance using the available current source, which is 4 ampere. Now what we will do with the voltage source, we will replace the voltage source with its resistance. Now we assume that this voltage source is the ideal source, so we will replace the ideal voltage source with the zero resistance, and zero resistance means that the voltage source will be replaced with a short path or short circuit, right? Now redraw the circuit. So after applying these steps here on the circuit shown previously, we can redraw the circuitry. So this is A, this is B and C and D and E, F, G and H. Now our purpose is to find out the current through 5 ohm. Now so let us assume that the current due to 4 ampere source in 5 ohm is I2. This is our assumption. And the direction is from B to C. So this is the direction. Means this current will come and will come to this particular junction B. It will divide into these two currents here. So this current is, let us say, I2 here. Okay. So our objective is to find out I2. Now what we can use? We can apply the current division rule. So I2 can be obtained by applying current division rule at junction B. Okay, so we can apply current division rule here. Now we can see that these two resistances are in parallel to one another. So the resultant here is 1 by 2 plus 1 by 2. So it is uh, 4 by 4. So it is almost 1 ohm. So it is 1 ohm here, right? So the sum of the parallel combination of these two resistances is 1 ohm. Now I2, how will we find out I2? So let us calculate I2 here. So I2 is equal to, let us apply current division rule. So I2 is basically, sorry, I2 is basically the part of this 4 ampere current, right? This 4 ampere current is coming to this junction, and here you are getting this I2. So I2 is equal to, as per current division rule, I2 is given by the 4 ampere current into the resistance of the branch where I1 is flowing. This one. So this is 2 ohm resistance here, because this particular branch is opposite to this particular branch. This one, it is in parallel with this branch. BG is parallel to BCF. BCF, right? This branch. So the resistance is 2 ohm, and then we will divide with the sum of all the resistances present in these two branches. Okay. Now, so this is our uh, 2 plus 5 plus 1. So it is 8 by 8. So this is 1 ampere. So that means the current in 5 ohm, that means the current in 5 ohm resistance due to the 4 ampere current source is 1 ampere. So mark it as, let us say, equation number 1, for example, and we will highlight this one. So I'll box this right now. So it is not that you have to apply the current division rule only here. You can apply any available method which you have, right? Any available method you can apply. You can apply nodal analysis or mesh analysis, whatever, whichever you find convenient. That is it. Now, let us come to the next step, in which we will calculate the current through 5 ohm resistance using uh, you know 8-volt source. Now, what we will do with the current source? So current source will also be replaced with its resistance. We will consider the voltage source now, and we will replace the current source with its resistance. And then the if we assume that this current source is an ideal source, so its resistance is infinite, and it will be replaced with an open branch. Now let us redraw the circuit. So after applying this, we have this particular circuit here. Now this is 8-volt source. We have to find out the current through 5 ohm resistance here. Now, okay. Now let us say this current, the current produced by this particular source is uh, the current produced is, let us say, I, for example. Then at this junction, this was B and this was C, D, E, F. What has happened to the current source? The current source will be open now. We'll keep it as open. Okay, so this was A. So A, B, C, D, E, F. This was G and H, for example. So this was the current source here. So we will not have any current here because this is open, right? So we will not have any current in this particular branch. So no current, right? Now this I current will come to this junction C, and let us say it gets divided here. Let us say it is I2 dash and it is I1 dash, for example. Okay, so this I2 dash current will flow and come to junction F, and it will meet with I, and then you have I current here, for example. So let us assume that the current through 5 ohm resistance due to 8-volt source is I2 dash, and the direction is from C to P. This is the direction, let us say. Now, how will we find out I2? So I2 can be, you can apply mesh analysis. Uh, we can use mesh nodal uh, current division rule, etc. Anything, whichever you find easy. That is it. There's no thumb rule here, right? So let us see how will we find out the current. We'll apply, uh, current division rule here. I'll apply current division rule here. So let us try to solve the network for I2 dash using current division rule. So I2 dash is equal to, now let us find out its equation. I2 dash is basically the part of this current I, which is coming from this 8-volt source to junction C, and this can be written as, so I, the main current, into, so let us see, into the resistance of the opposite branches. Now this I, and this I current is dividing at this particular junction C. We have I1 dash and I2 dash and I1 dash here. So I2 dash is I, the main current, into the resistance of the branch parallel to this branch. No, we have CF. Now CF is parallel to CBG branch, this one. So we will multiply this I with 2 ohm. It is 2 divided by, now let us see, sum of all the three resistances here, means in these two branches you have these three resistances. So we have 5 plus 2 plus 2. So this is, let us say, equation number 2 here. Now to calculate I2 dash, we need I, right? I is the total current in this circuit, sorry, due to 8-volt source. Hence, I is equal to 8-volt divided by R equivalent. Now, R equivalent is calculated across the terminals D, E here. So we will calculate the R equivalent across these two terminals so that we can get the value of I here. R equivalent is equal to, let us see what is R equivalent. So now we will simplify this circuit from this end to this end to calculate R equivalent. So here we are calculating R equivalent, right? So it is 5 plus 2, both are in series. So 5 and 2 are in series. and the resultant is in parallel with the 2 ohm resistance, and the resultant is in series with the 2 ohm, right? So it is 7 parallel 2 plus 2, so it is 14 by 9 plus 2, and it is 32 by 9 ohm. So this is R equivalent. Hence I is equal to 8 divided by 32 by 9, so it is uh, 9 by 4 here. Now we can put this value, this is, let us say, 3. Hence I2 dash is equal to 9 by 4 into 2 divided by 9. So this is 1 by 2, that is 0.5 ampere. So the current in 5 ohm resistance due to 8-volt source is I2 dash is equal to 0.5 ampere. Now we will find out the total current. Okay, now let us see the direction of the current here is from C to B. It is from C to B, and in case of the current source, it was from B to C, right? So the net current basically in 5 ohm as per SPT. So let us bifurcate this one. So as per superposition theorem, the net current is I2 plus minus I2 dash. So we will see the direction. So I2 was from B to C, and the value is 1 ampere, and the current I2 dash was from C to B, and the value is zero point 0.5. So we will take it as minus 0.5 because it is opposing the standard direction which was assumed by us. So it is equal to 0.5 ampere. Now this is how we can find out the current through any branch using superposition theorem. Now superposition theorem has certain limitations, and the limitations are that we cannot apply this theorem in a circuit which has only one source. So to apply this theorem, the circuit must have two or more than two sources. Then second limitation is that this theorem cannot be applied on the non-linear networks. This theorem cannot be used to calculate the powers in the electrical circuit because power is equal to V into I, and this would give you a non-linear relationship, right? Because P is equal to V square R or I square R. So when it comes to square, so this becomes non-linear here. Then uh, if we want to analyze the highly complex networks electrical circuit, we should not use this particular theorem because it would be more complex to use this theorem on the highly complex networks, means which has more than large number of electrical energy sources. Now this is it for today's lecture, guys. Thank you so much.